Hello, everyone. My name is Betty Howard from STERIS. I'm the Senior Radiation Sterilization Manager here. I thank you all for calling in or watching our webinar today. Our topic will be photon technologies. Specifically, we're going to look at gamma and X-ray. Not to discredit any other ionizing technology, but most of the questions we're seeing this time versus the last time I did a seminar for PDA were focused on the photon technology. So we're going to pay more attention to that today. What we're going to look at is why suddenly everybody seems to be very interested in X-ray. We're going to compare X-ray and gamma since they're the two technologies that are the most similar to each other and used in the same ways. And we're going to look at similarities and differences. We're going to end with looking at any changes in the validation processes or technology transfer, meaning moving from one technology to the other. And at the end, I list a large number of references that support things I say in here and that are all free access online. So they should be easy to find if you want additional information. That's me. But I've already told you who I am, but my background is mainly in ionizing technology, so E-beam, X-ray, and gamma, specifically on dose setting methods and materials compatibility. Okay, so why are we here today? Why X-ray and why now? Well, part of that comes from the great success all of you have in healthcare. There's expectations that the need for gamma, which is the largest used ionizing radiation of the three that are known, is expected to grow significantly in the near future. All projections show that the growth of industry, the growth of need for the technology, the growth in the number of products that will be needed every year to be produced and as a result also sterilized is expected at minimum to grow 5 to 8% per year, but many projections in more recent years are saying as high as 10%. Remember, any estimate and any reference article on this is subject to changes because of unplanned events. We all are very aware what an unplanned event can be. We went through it for several years with COVID. To prepare all of us for the growth of the industry, the growth of healthcare, the growth of the need for the supplier of parts, services, manufacturing capabilities, quality, all of us have to work together, and all of us need to make plans. Even if you are a manufacturer, you may be needing to make more and more product than your existing manufacturing facilities can handle. You may need to build extensions or build more facilities. You may need more than one supplier for a part. You may need a supplier that can make more than the one you're already using. And all of your services, such as laboratory testing and people like us, who are the contract sterilizer at the end of the process. We need to plan now because of what may need to be built or constructed or made effective in the future to cover that growth potential that you guys are all going to produce. That means to do that, we are going to ensure that the continuity of a sterilization process for all of your critical products can be achieved. Part of that system is why X-ray, which has been around just as long as the other two technologies, E-beam and gamma, is being talked about more, and we're going to cover why. Now, when you start looking at any limitations you might have on availability of a sterilant, you start looking at what your alternatives could be, or what additions you can make to your existing sterilization family of processes. But think first, what does that alternate technology have to do? What does it need to be effective? It needs to be something with a lot of processing potential. It needs to be able to grow at the rate to meet these projections and respond to any unusual demands or the development of new products that have not even been projected yet. Ultimately, can it provide the continuity of critical healthcare supplies needed for all of our health and business needs? We're going to talk about photons today, but you can never separate in ionizing radiation that you need to know what an electron is and what a photon is. Even though we're not going to directly talk about E-beam, it's related to X-ray very directly. When you have an electron has mass, it's a particle, and that particle has a charge. That very heavily affects its interactions with other materials. And as a result of that, it will not have on its own as good a penetration depth into a stack of product as a photon will be. A photon has no mass, no charge. It's short, intense wavelength of energy, and it can be produced in more than one way. It can be produced with electricity, just as electron beam is, but it also, and more commonly to most of you who are already familiar with radiation, probably are thinking cobalt-60 as the source material for most industrial sterilizations with gamma, with photons. The important thing about a photon is it's not easily stopped because it has no mass or charge. So it has no electrical field around it, no charge that would interfere with its ability to penetrate. So it will have really good penetration through even relatively dense materials. In both cases, an electron or a photon will lose its energy by ionizing other atoms in the system. Okay, first we're going to look at gamma. This gray area on the one side here is we call it a bunker. That will contain the radioactive source. It will contain the area where product will be exposed to that radioactive source and still protect people who are outside of that bunker. It has some very obvious parts to it. That blue rectangle in the back is where the cobalt-60 is. When product is being sterilized, the cobalt-60 would be lifted out of that storage pool of water underneath the floor. Notice even the pool is surrounded by heavily reinforced concrete so that it's protected while the source is down there, but the source is also shielded by the water as well. Those gray boxes you see around that source material are the containers that will carry your cartons of product as they move through the system and then back out to be returned to you. If you look at the little squares at the middle, that is like the stepwise fashion that those carriers will take. They will enter at one point. They will be scheduled to move at a certain rate, stepwise. As they move forward, they will dwell in a particular position until it's their turn to move. They'll move to the next step, the next, and their job is to go to every position in the irradiator before it can leave the irradiator. This is the most common path to gamma radiation in the US and North America. You do see some that are like the other picture on the reverse side of the slide. That is a pallet irradiator. Those are more commonly used from what I've seen in Asia and Europe. But either one will deliver the photons from the gamma, and they will all move around the source to achieve a uniform distribution of dose to your product. Now, cobalt-60 is what we use almost exclusively these days in industrial irradiators. There are other types of materials that produce gamma, but cobalt-60 gives you very high activity amounts, and it has a reasonably long half-life, sorry. To create cobalt-60, which you do not mine, cobalt, the atomic number, if you look on a periodic table, will be 59. To get 60, you have to have neutron bombardment, so you need some kind of accelerator system to keep pounding the nucleus of the cobalt-59 until you can achieve the addition of one more neutron. As soon as that happens, you start a decay process because you've created something that is unstable. We call it radioactive. When it's unstable, it's doing everything it can to return to a stable state. And in doing that, it creates something that's very useful to us, which is the two photons off to the bottom of the screen. They have known energy levels, 1.17 and 1.33 MeV for an average of 1.25, and MeV, million electron volts, is how energetic they are. When you look at X-ray, this system, if you are familiar with E-beam, will look very similar to an E-beam system because for the most part, its basic design is an E-beam system with one critical difference. You start off on one end of the system, that thing that looks like a little spaceship in the back. That is where electricity would come in. It will interact with a cathode, frequently covered with platinum. The electricity will cause electrons to be released from the cathode. And then the rest of the system, everything here under vacuum, will move the electrons forward towards that V-shaped thing at the end with the yellow line on it, which is called a scan horn. It's important if you create electrons, because they are charged, they have to be kept under vacuum, because any interaction with another molecule, such as oxygen, they will dissipate their energy and they will never reach the exit of the irradiator, which is where that scan horn is. When your product is being processed, those electrons are created, they're accelerated, they're focused into a very tight beam. By the time they get near that scan horn, they are moving close to the speed of light. So they are very energetic. That very tight beam will also, when it gets toward the end, there are magnets that can focus it and move it around. What they will do is they will oscillate the beam back and forth as your product stack is passing by the scan horn. In doing that, as it goes by, your product is collecting kilograys of dose, just like it was collecting from gamma. The kilogray is a kilogray, dose is dose for both of them. And in this case, both of them are photon sources. If you look at the little drawing on the side, I want you to look at the stack. That stack is the size of a pallet. So as you come through here, the electrons come out of the scan horn, and now's where the difference occurs. Right at the end of the scan horn, there is a metal plate, frequently made of a metal called tantalum. When those electrons hit that plate, they cannot get through it. They dissipate their energy into the plate, and you create something that's called Bremsstrahlung, or breaking energy. To us, that's called an X-ray. The important thing is to keep in mind what is happening with the photon as it's created and as it's used. This next slide shows you that. The photons from gamma are represented by the blue arrows at the bottom. We call that isotropic distribution of photons because those photons are coming off the source in every direction, back, forward, up, down, every angle. As the product is decaying over time, so it's a 5.7-year half-life, a loss of activity of about 1% a month if you don't put more energy into it. These photons are coming off in all directions. There's no on-off switch for this. This is radioactivity. If you get a hold of radioactivity, you can't put it in a storage cabinet and just keep it and expect it to be as energetic as it was the day you put it in containment. So we have to use these photons as soon as we make them. It's a stepwise decay, and when you get to full decay, your cobalt-60 keeps its atomic number because it's not going to kick out the neutron you just put into it. But now, if you look at the periodic table, you'll find 60 is actually nickel. For X-ray, the spectrum of the energies of those electrons, of the photons, sorry, is much broader than in gamma. Gamma, 1.17, 1.33 MeV for an average of 1.25. In gamma, they will be much wider distribution, many of which are lower energy than even gamma, but a portion of that spectrum will be much higher energy, closer to the energy of the system. The important thing to remember is that they are coming off that scan horn in a direction. They are not isotropic. So what you are going to see in these systems is you will see at least two-sided passages so that you can get good distribution all the way across whatever you're presenting to the source. And the photons will move in similar directions that the electrons did. The electrons, the photons or the electrons, they are only ionizing product when the product is in front of the scan horn. Once it moves away, it's no longer being ionized. Also, these are created by electricity, so there's an on-off switch. When the process is not needed, it can actually be turned off. Okay, when you start looking at that, remember what you've got now. You've got photons, no mass, no charge. More than 90% of the photons created for out of X-ray are much lower energy than gamma, as low as 0.3 MeV compared to that 1.25 MeV for cobalt. A percentage of those X-ray energies, though, are as high as 7 MeV, which is the energy of the system. The gamma ones are isotropic, always on. X-ray ones can be turned off. And the photons are propagated from the converter plate in the general direction of the incident electrons hitting it. Okay, you can design X-ray machines similarly to how you design gamma systems. You will frequently hear people refer to a gamma radiator as being source overlap or product overlap. That is a description of the position of the product relative to where the energy is coming from. In an X-ray system, you can also have product overlap or scan horn overlap. Now, if you look at the piece in the middle, that's your scan horn. The little box there, that's palette of product. The blue indicates where energy has been absorbed. What I want you to focus on in this particular system, which is product overlap, meaning the product is higher or lower than the scan horn. That's okay. You do one pass, you turn it 180 degrees, you do another pass. Notice now that you have at least half of it with some pretty uniform dose. In these types of systems, you can lift the palette onto another level. Now the source overlap is at the top, and the product overlap is at the top. You run it past the source rack, and then it gets another corner of it done, 180 degrees, the fourth pass. If you look at that, that distribution of the blue is now very, very uniform, and that's what you're looking for in sterilization technology, so that you don't have a broad difference between your min and max dose. This is the picture of the scan horn in our newest opened facility here in Libertyville, Illinois. This scan horn is about 9 meters high. It allows for even stacking of pallets, so it has the ability to now run as source overlap. So the product mix will be lower than the top of the actual scan horn. If you look at an overview of what X-ray is, most of what's written here will describe your standard E-beam system. You're generated from electricity. They are accelerated to gain the electrons are gaining energy as they're accelerated. The electrons are generated in a vacuum. They start from the source, the electron gun, which is where the electricity is. The electrons are drawn away from where they were created toward where the product is as they're accelerated. When they leave the accelerator as a cylindrical beam of energy, that beam is oscillated to produce the scanning effect as the product is moved under it. And that's when it's going to leave the vault. But in the end, here's where the difference is. When those electrons that are created hit the converter plate, they are no longer electrons, they are now photons. This is to remind you there is a plug and there's electricity involved. But the difference between the X-ray system and the E-beam system, all you have to do is look at that product stacked underneath. With X-ray, the photons have the ability to penetrate much deeper, so you can have a larger stack of product than you would have with E-beam because of the charge and the mass of the electrons. Okay, we're going to look at similarities and differences. Similar, they both use photons. In both cases, we're measuring dose in kilograys and measuring how many kilograys with some form of dosimetry. We don't use BIs in radiation. It's an ionizing radiation source. In this case, in X-ray and gamma, the dose is coming from the photons, but also something called a secondary electron, which is going to be in a future slide. The effectiveness of a photon or an electron, whether it's from X-ray or gamma or E-beam, is the same. They still create a certain number of kilograys that have to be achieved in your product in order to deliver the dose that's effective for your sterilization process. We usually just call that dose is dose, or more formally, dose equals dose. So a kilogray of E-beam, a kilogray of X-ray, and a kilogray of gamma are the same. The mode of action on a biological molecule is the same. So killing things works the same way, whether you're doing any one of the 3 ionizing technologies. The guidance of how you set a dose and assure that you're getting the sterility assurance level you desire follow the exact same ISO standards. They use the same dose tables in the standard. There is not a separate dose table for gamma, E-beam, and X-ray. There's one table for ionizing radiation. The differences will be the energy levels. You saw that on those earlier slides, how many MeVs of energy they have, the source of the photons, but also now the rate at which the photons, or at the rate at which the kilograys that are being delivered to your product are being delivered. X-ray is faster to deliver the same amount of kilograys than gamma. E-beam would be faster than X-ray. Because of the way the dose is delivered in X-ray, the temperature achieved in the product, or the amount of exposure to elevated temperatures over room temperature, is expected to be less in X-ray because you spend less time in the ionizing field because of the increased dose rate. So that's the next comment, that the exposure time is different. Gamma is measured usually in kilograys per hour. X-ray may also be kilograys per hour, but will be many less kilograys to deliver the same amount of dose. The ability to process in a pallet versus a carrier or tote, and that difference between being accelerator-based and radioactive-based, especially as people are trying, in many cases, to move away from radioactive usage. Now, I mentioned secondary electrons a couple of times. All three ionizing technologies create ionization. Ionization means the loss or gain of electrons. So if you cause an ionization in a product, which a photon or an electron will do, it causes what's surrounding it, when it makes that collision, to release electrons. Those electrons will now ionize the next atom over from them. Those atoms will also release electrons, so that you're propagating this flow of electrons throughout the matrix of your product, in addition to the initial energy you put in, whether it's a gamma or an X-ray. Deep penetration, lots of collisions as it's going in. So there's lots of ways to initiate this flow and creation of secondary electrons. So regardless of the source, electrons are part of what's going on inside your product. Okay. The radiation references that are used to sterilize a product are the same. The most commonly used are the first three groups, which are the 11137 documents that tell you how to set a dose, what's required to set a dose, how to map the product. The next two are microbiological methods to measure bioburden and sterility, which determine what your dose should be and how to test it for effectiveness. And then the fourth one on here, 13004, which started its life as a TIR and is now a full ISO, gives you additional dose setting methods that are not already covered in 11137. The rest of things here are TIRs, technical information reports, that give you additional information to help you achieve what you need to do to make those requirements for a sterile product. The most commonly used TIR worldwide is TIR 17. It is a guidance document on the effects on materials of different forms of sterilization. It's actually, as we speak, being put into final format to be released as an updated edition. But it doesn't tell you exactly what dose will work for your product, but it gives you an idea of the effects of different types of sterilization, not just radiation, on materials you might commonly use. The rest of these are modifications to some of the things that are in the existing ISO documents, but they may give you better guidance on how to achieve the requirements. And they develop over years, and many times they go away because the information in them is incorporated into the next revision of 11137. The most important ones for what we're going to talk about today will be that TIR 104, which will come later in the slides. Always remember that the things you had to do to validate your product do not change. In addition to dose setting, you will have packaging concerns and testing for the package. You may have biocompatibility that you have to test for. You may do risk assessments on your device. But also keep in mind, these are true of all products that are sterilized. Regulatory acceptance, people were very worried when they heard X-ray. They said there isn't a standard for X-ray. There doesn't need to be a separate standard for X-ray because it's covered by the existing ionizing radiation standard, meaning the 11137 group. What we used to call traditional now is called category A. So all the commonly familiar sterilization methods, in addition to radiation, are covered as traditional. They have standards that tell you how to use them. Novel or newer technologies are classified as novel or category B because they don't have those standards yet. The other things like 13485 requirements, GMPs that you have, the acceptance with Xray is the same. The other similarity is what I affectionately call dose is dose, microbiological effectiveness. It doesn't matter really, if you think about it, how you sterilize product, but the important thing is whatever you use has to be effective. So the microbiological effectiveness of what you're going to do has to give you the expected sterility assurance level using the requirements of, for example, ISO 11137. In the inactivation portion of this, there are many papers that have been published. Probably the earliest ones with the most detail were done by Alan Talientire and Arnie Miller in 2010 and 2015. They did a lot of work with biological indicators, showing when you did gamma, you did E-beam, or you did X-ray, that you didn't get dramatic differences in the effects. There have been many papers done since then. Some of them are listed here. There was work done with Ariel France, who is a dosimetry company, and Steris Switzerland, which is our first X-ray system, as well as a paper where many different companies, that Bryant and Hansen paper, Traby Bryant and Joyce Hansen in 2020, that covered lab work done by NAMSA, Baxter, and all these groups worked together to show that if you inoculated things, you could get the same kill at the same dose. The last one is more recent. Brian McAvoy is from Steris. There's a long list of people who are contributors on this. And the Steris paper, or the Steris contributing paper, actually did some work to compare the work of Alan Talientire with current systems, meaning the energy level of the current X-ray systems and E-beam systems. Radiation processes are all qualified in accordance to 11137. They are dose based on bioburden, not on the type of ionizing radiation used. The ionizing radiation is telling you how many kilograms of it you need to kill the bioburden. But the bioburden is what's deciding the dose number, not whether it's X-ray, E-beam, or gamma. Lethality, the more complex you are as a living thing, the more things that can be damaged, and the easier, sadly, is you are to kill. If you think of what's going on in all these biological systems, you have enzymes, which are just fancy proteins that do some function that keeps you alive. They're involved in metabolism, respiratory. They're involved in repair when you're cut or wounded. They're involved directly in replication, or whether something is sterile or not is frequently regarded as whether or not it can reproduce. If you damage the source material that contains all the information for you to do it, it will not be able to reproduce. It will not be able to repair itself, but it also it will bit by bit lose all its function, and you will die, or the organism will die. Here's an example that's a direct side-by-side. We look at DUR, dose uniformity ratio, which is the maximum dose delivered versus the minimum dose. We look at that as a way to see how effective a process is. In this study, they did the exact same pallet configuration of homogeneous product with both a gamma and an X-ray machine that they had both of them in Switzerland. And when they did that study, they got an improvement in the dose uniformity, significant improvement with X-ray. This is not to say that you will always get that level of improvement, and there are things you can do to improve the overall comparison. But it means there is a potential here that, like for like, you can get improvements in dose uniformity. It's important to know that when you're doing this on X-ray and you're doing things on pallets, the pallet dimensions are important. You can't take a pallet, for example, that originated in Europe and run it on an American system. You have to keep track of the size, because it has to fit on those tracks that are in this picture. You have limits for height as well as weight. Whichever one you reach first limits how much product you can have on your pallet. They're not dramatically different in size and weight, but you do have to always know, otherwise this will not flow freely across the tracks that are used to rotate and move your product. Now, If you look at all the things that are alike about them and the differences in how they would affect your delivery of dose or the effectiveness of dose, the first thing that does come across to most people is, can I change between these technologies? And the answer is yes. It was actually already described in the standards long before people were, to be honest, heavily interested in X-ray, because they had systems that worked. They were growing at a rate that everything was fine, and they never hit any delays or limitations on what they could do. As things grow, we have to plan ahead for what that volume will be. The steps you would need to transfer between a technology, you're basically using to document what we already expect to happen, that the effectiveness is the same, that the minimum dose will not change, that the maximum dose should not have to be affected, and that the distribution of dose within the load will be the same or better. The one difference will be the term activation, which we'll also go through. That will be reflected in X-ray only of the three. ISO 11137-1, which a lot of people don't read. They always go straight to 2 because that's where your dose tables are. This is the one that tells you what you can do and how often you have to do things to be a validated product. Validations are not one and done and then you do nothing. And if you remember nothing about where these things can be found, they're all in something called Section 8, between Section 8.1 all the way to 4. And they all cover what the guidance is from ISO in terms of transference of a maximum acceptable dose, your verification dose used to substantiate your sterilization dose, and the sterilization dose. If you read these things, they always start out with the worst thing first. And I think that's good because they're making you pay attention to what the exceptions might be. When you're looking at the verification dose, they tell you you can't change source. It says unless. And the first thing it says in terms of unless, how do you demonstrate the effectiveness of your dose in the existing system you have? In radiation, that's always the use of dose audits. Retesting the effect of your verification dose to see if the current manufactured product is still responding to dose the same way. So in effect, you can show microbiological effectiveness by doing a dose audit. Again, we're back to it's bioburden that's setting the dose. So if the bioburden is not changing, the dose should not change. If the dose is not changing, your verification dose will be as acceptable as it was when you validated the original method. So if you're going gamma to X-ray, you're not resetting the minimum. Also pay attention in 11137-1 to the annexes of the sections that are also in Section 8. So A refers to it's in Annex A, and it's Section 8.4 from the original guidance. It gives you more detailed information than the standard does. As things over time changed, many times additional information was added to the annex, helping you understand what that requirement line may be. There may be a single line in the actual text of the document that tells you what to do, but it frequently does not cover all of the current things we think about products and their needs. So it's always advisable if you're changing something to still check your minimum with a dose audit, but there may be other things that you will have to test because of the needs of your product. Maximum dose, still in Section 8. First thing it says is that you are required, because it says shall, to establish a maximum acceptable dose. This is not something you do later. It's not something that you do after you've done your validation. It is part of your validation. You have to be able to show that the maximum dose you will allow a product to have still gives you a product that's safe, effective, meets your specifications, and provides the product's stability through the life of its product, which means the lifetime or expiry date on your product. This is true of any ionizing radiation, not just gamma and E-beam, gamma and X-ray. The transference of dose of your maximum acceptable dose between sources, it tells you you have to demonstrate the differences, which means you do have to test it. Most people have a great deal of data on the method they first validated, for example, gamma. That testing will guide you into the best test to do to evaluate the newer technology, for example, Xray. This is called a risk-based approach to coming up with a test plan. And now this is where we're going to transition into that document I mentioned that we were going to have to pay attention to. When you're trying to do these changes, it can be very confusing when you read 11137-1. Not because it's not well written, it just doesn't seem to cover everything you want to know or the questions you may have. TIR 104 was written about 2 years ago to try to focus more on that transition, to give you guidance on making those decisions of what I have to do when. But remember, when the original document was written, healthcare products now may need to be sterilized in multiple facilities. Maybe back 20, 40 years ago, 30 years ago at least, when the wording was put in those standards, people never even thought of processing in multiple facilities. You may have products that as they grow need to use different ionizing sources because of their needs of volume, or if one facility is not operational or that can't handle the amount of volume you need immediately, you may have to use more than one ionizing source. What the beauty of this document is, it gives you guidance on what you have to do to meet the requirements of those standards transferred. Now, there's a lot of information in here. We clearly cannot cover all of that today. It gives you information on transferring like for like, one gamma radiator to another, one E-beam to another, or an X-ray to an X-ray. But it also, and probably the biggest contribution for most of our needs today, is this last part. Gamma to X-ray, gamma to E-beam, E-beam to X-ray, or any one of those the other way around. Nobody says you have to go from gamma to X-ray. You may go from E-beam to something or gamma to something else. That is your choice, but it does discuss in terms of rationales, explaining some of the sections of 11137, supporting clarification that may help you get to what you need to achieve. But probably the most value is that one in the middle in blue is the flow charts. There are 3 key flow charts in here when you're transferring. Figure 1 covers the first one, which is process capability. People sometimes don't think about this one. First off, your product, your cartons, have to be able to fit in the second technology you want to move into's system, physically fit. Sometimes if you're changing from something that's in a carrier and now you're going to something with a scan horn, you have to consider that your boxes have to clear the scan horn and be within the range of where they are actually being irradiated. So fit counts. You may have to change slightly your max dose if you go to a technology that's lower in penetration. For example, going from gamma to E-beam, you may have to slightly increase your max dose. You may not. It'll be very dependent on the system you use and the density of your product. The dose uniformity, that max to min versus your product density, tells the plant, when they determine that through something called dose mapping, whether that product you want to process in their irradiator is likely to be successful. But what these various changes that may be in your product or the way it's presented to the source, the big question is what results you get. Are they significantly different? And only you can judge that based on your criteria of acceptance for any particular parameter. But the nice thing about here is each one of these figures that I'm just going to mention, they give you steps when you're evaluating something as to what's different. Is this different? Yes or no? And it tells you which direction to go about what you should be doing in terms of testing. The figure 2 looks at the transfer of the minimum sterilization dose as well as the verification dose. Has the product changed at all since it was validated? Does the product support microbial growth? Do I have to be considered about moving my product because of the time element? If the product contains water in the system, when you did your original validation, you had to work into the time from manufacture to sterilization, that presence of water in terms of its effect on bioburden. So if, for example, you changed your location of where you were going to process and it was going to dramatically change your time between manufacture and sterilization, you would have to consider that Could it impact your bioburden quantity? And if it does it change it enough that it would change your dose? That again can be assessed with a dose audit. Figure 3, transfer of maximum dose. It gives you guidance as well, steps to go through. I will say though that no matter what you're doing here, the important thing about max dose is it's giving you your range. Your min is going to be based on your bioburden. You won't be able to change that. But the max gives you the ability to process it. What we do in a plant is we do dose maps or PQ maps, product qualification maps, to show that how you're going to present the product to us, can we achieve the dose range you want us to achieve? Now, keep in mind that there are little comments that will appear through the ISO standards that give you some guidance on the significance of certain events. Since a change to X-ray or E-beam versus gamma will impact the dose rate, it could impact the temperature that the product sees when you change from one modality to another. Will those changes impact degradation of the materials in your product? The one statement they make in here that actually helps this make it not as big and impressive as a comment of a hurdle to overcome is that changes that move from a dose rate that's slower to one that's faster, so for example going from gamma to X-ray, are not expected to have significant impact on the degradation of the material because of that time in the ionizing field, which is related directly to oxidation. Most material changes are related to oxidation. Okay. Now here's just an example. It's not meant to be the perfect comparison of doing risk assessment. You look at some of the criteria that you're concerned with and then relate X-ray versus gamma. How much of a risk is it to change? The minimum dose for sterilization is equivalent. There's no risk. The dose rate is higher in X-ray, so that would be expected based on the standards and the guidance of 11137 to have low risk, if anything. Temperature would be expected to be lower versus sitting in something where you're at elevated temperature for longer times where it would have more exposure to temperature. No temperature will be achieved the second it goes in to go to the highest temperature possible, but remember it will be in the chamber for the time it takes to deliver the dose. The exposure time will be less, which just like the dose rate, because they're directly related, would have low risk. DUR, that dose uniformity, max divided by min, in X-ray is usually better or at least equivalent. So it's not seen as a barrier or a risk. Product handling, because in X-ray you're now doing these things on pallets. You may have, when you design the product, you may have come up with the perfect way to package it and transport it to make it get to its destination safe without damage. When you would normally do gamma in a carrier, when that pallet came to us, we would take the boxes off the pallet, put them in the carriers, and then put them back on the pallet. In the case of X-ray, so there's much less handling on your product, so less possibility that anything could be moved or changed. So what does all that mean in terms of what happens to the materials in your product? Well, in X-ray, the dose rate is faster. Faster dose rate means lower ionization exposure time. Lower ionization exposure time means less oxidation, which translates into less negative effect on the materials. When you do risk assessment, make sure you look at the criteria that are important to your product. Write a test plan, a design. Define the tests you're going to do and why those were the ones you tested, but also what your acceptance criteria will be for any of those tests before you actually run the test. Ideally, do a side-by-side with the same lot, the same dose, both technologies, if you can, if the product is available. Know your current product's effects. How was the maximum dose determined? How did you decide what technology you were going to use to assess the product and to sterilize it? That information is very valuable because it is the basis of any comparison you make to an alternate technology. Leverage everything you know about your product's effects to sterilization and what things are important and critical, but then you can also use publications and seminars to help you design plans, but not to replace the need for testing. Big question when you get down toward the later parts of this, you wonder, well, is X-ray a viable addition or alternative to gamma? And the answer is yes. They are both photon-based, so they have deep penetration needed for the current density of your product. They're non-radioactive, so you don't have that annual replenishment of the isotope in a gamma radiator, so no delay. There's no week where you'd be off ability to process. It has the on and off switch. If we don't need it, we can turn it off. We're not wasting anything. It has a constant dose rate. When the product is moving past the scan horn and past the converter plate, the ionization is only that time when it's passing through there. In gamma, you do that shift dwell process, so you have actually different dose rates as you accumulate dose, but that's okay because dose effects are cumulative. As you saw even with X-ray, when you had multi-passes, you are adding dose as you do each pass. The cumulative dose is the one that is sterilizing your product. You can process in pallets, so there's less handling and transport and in processing. The technology equipment, honestly, took advantage of the fact that people didn't see a need to go to X-ray when they were happy with what they had. But now as we start looking for more capacity, the equipment has gotten better and more reliable than older systems and has many more ways to monitor what it's doing. Those effects in terms of oxidation that we already covered, and the fact that they are not, X-ray is not a novel technology. So yes, it creates more capacity. It follows the same ISO standards as the gamma did, same mode of action on organisms to kill them. Use multipass systems either way, whether you're going around it step by step, or if you're going past it, turn it, and going back for. If you're valid in gamma, you have the data you need to make a really good test plan and have the data to compare the results of both technologies directly. As a result, you will see, and of course I use STERIS examples because they're the ones I know, but you will see across the board in healthcare, people are adding capacity in order to sterilize products and to test products. We are no different. If you look at the colors of those circles, they represent either different technologies or the building of laboratory space to accommodate all the needs of healthcare growth in the next 5 or more years. Along that line, in terms of what we're building, they are being built globally. The one in Libertyville just recently opened. There will be another one in Ontario, but there will be others that will come down the line, such as the ones listed here. Okay. All of the things I used in here to support what I said are all in available documents, most of which are free access, so you can find them by just looking online for them. And if they're not totally free access, if your company has representation in AAMI, the AAMI documents, these industrial sterilizations, are compilations of many articles that give fantastic articles that explain a lot of the concepts I've talked about today. So they're on minimum dose, on maximum dose. The 2 things I haven't talked about yet are the need for a map. When you change an irradiator, you have to assume that 2 irradiators are not identical. So you have to have some way to compare them, and that's that map, where they look at the distribution of dose across your product matrix in the presentation that you're going to give it to go to the irradiator. So if it's in a pallet, if it's in certain boxes, weight and size of those boxes, all of that can be taken into account to show if your dose range can be delivered, not to show if it's sterile on its own. Just doing a map without a validation of dose tells you only the distribution of dose. It does not tell you what dose you had to have. Now, this is true of any of the technologies, not just moving from gamma to X-ray. What is a map? Really, a map, and that's, you'll notice this is a really formal definition, but that's okay. Obtaining and documenting evidence that equipment, instrumentation as installed and operated in accordance with the operational procedures of the facility consistently performs according to predetermined criteria, meaning does that equipment we have work the way we expect it to? The results are specific to an irradiator, not to a company that irradiates, not to a location that may have more than one physical irradiator, but to an irradiator. It's specific to the process load configuration that you will be sending us. If you change the load, you may need to do an additional map. You can use simulated product versus real product, but the choice of the simulated product in any map has to attenuate and scatter properties that are similar to those of the real product. Some people use expired products. Some people use product that was slightly damaged in manufacture. The more closely that the product used for a map relates to your product, the better results of the mapping study are. Now, the one I said that we're going to save till the end is activation. Activation means the potential to create a ionized state, or for want of a better phrase, activate, make something radioactive. In the case of very high energy systems, like E-beam systems that are run over 10 MeV, or X-ray systems currently in the standard says over 5 MeV, they ask you to assess the potential that the materials in your system could activate. When these types of things do occur, they are usually extremely short-lived, seconds to less than 2 hours, so they never would become a hazard to anybody using it. The question is not just if it activates, but is the total activation, because the product itself may already have some level of activation based on its materials. If you irradiate it at the worst case dose, will you create something with your product that would exceed the allowable limits for activation? To date, the testing we've done, and our facility in Switzerland has been operational for more than a dozen years, we have not found a system where it could not be processed because of a consideration for activation. Now, if you want to go into the details of the physics of activation and of the systems that are used to measure it, this article in the industrial sterilization thing from Amy is excellent. The authors are people from STERIS. There's a really good physics consultant, and Thomas Cox from Fermi National Labs in Illinois. What we've got here today, what we've talked about is the radiation processes we know, we accept, can be used to sterilize products. The dose required through dose setting activities are there to give you the minimum, but also they force you to test the maximum that the product can tolerate. The dose delivery systems vary with the technology, but they can all deliver the sterilization dose you need, the minimum and a maximum. It may be that your product could be run in all three just as effectively, but you may find that one or the other is more desirable to you. Dose distribution throughout a load assures that the minimum required dose is achieved to every unit in the run, and that none get higher than the maximum allowable dose that you set, and that distribution is confirmed with the map. When you transfer, consider minimum dose support with a dose audit, with the existing validated verification dose. Map your product in the irradiator you will be moving to or will be considering as an alternate. Confirm the effects of the maximum allowable dose by comparing it to the existing information you have with the existing technology. It's possible with X-ray that max could be slightly lower in X-ray than it was with gamma. I always tell people test the like for like, because that's the data you already have for the one technology. See if you can get the equal result with the other. If you want to, or it's allowable and you would prefer to move it down, you may be able to. I can't tell you you'll always be able to go lower. Design test plans with your current knowledge in mind, using current publications as well to support your ideas. Assure that all known requirements for documentation for your product specific to regulations are met. You may have things you have to do because of change control in your system, your SOPs, or for specific requirements in specific countries. Clearly, I cannot give you every possible variation, but you already know what those limitations are for your product and assess activation when you use X-ray. All of our current e-beam systems are all at 10 MeV, so those you will not have to test in e-beam. Gamma, the energy level is much lower than 5 MeV, so you don't have to test that. It will only be tested at the maximum dose with X-ray. Now, you don't have to do this for every batch you make. It's only to test that the materials in your product, as they stand, are not being affected adversely. Okay. I thank you all for listening to this. This is my contact information. Feel free to contact me with any questions. I know this was a lot of information in a very short period of time. And I thank you for your participation today.